clearly, if you draw the shear force, sorry, the reaction, solve for the reaction forces, you'll end up with P divided by 2, P divided by 2 because of the symmetry. When you take a section, so this is FPD to get the reaction forces. This is your free FPD for M and V. Fp divided by 2. Clearly, this point would have a moment and a shear force. Okay, and what we're interested here is what's going on in this here, over here. We want to compute the stresses here. Now, as a general rule, V induces shear stress. Okay, think of one surface sliding on the other. That's the shear stress. So V actually causes a shear in the sense it'll cause the left side from slipping over from the right side, right, along that surface I've shown. The moment M induces normal stress, which I think is kind of interesting. How can a bending moment induce a normal or an axial force? That's because, so this is not very intuitive, but it becomes more intuitive when you look at it this way. When you take a beam and you apply a pure bending moment M, it actually twists like in a convex shape like I've shown. So what happens is the top part shrinks in length, because you can clearly see that it is now going to, if it's a circular shape, then a part of an arc of a circle, then clearly the circumference, the length of this part is going to be smaller than the length of the outer part, and this part actually expands in length. This line is unchanged. Okay, you might have seen this called, it's called blanking on the name. It's the neutral axis of the beam, right? Now, when that happens, if the bottom part is going to expand and the top part is going to shrink, one way this you can think of that happening is if you apply an axial force, a normal force, then clearly when the force is tensile, you'll expect something to increase in length, and if it is compressive, it'll expect it to shrink. So what's happening here is you can infer the stress based on the strain being the change in length. The top part is shrinking, which means that there's a compressive normal stress, and the bottom part is expanding, which means there's a tensile normal stress. So this part, the top part, is under compressive normal stress. Okay, normal means sigma, and the bottom part is under tensile normal stress because it's expanding. Again, this is sigma. So this is how M, which probably has nothing to do with normal stress, is actually inducing normal stress. We can infer it from the change in length or the strain. Okay, we'll get more deeper into this. Sigma and tau are the terms used. Sigma is normal stress due to M. Tau is the shear stress. Tau is the shear stress. This is due to V. Okay, both have same units. It's force per unit area. So in SI units, this would have Newton per meter square. The other unit we'll be commonly using is FPS, pounds per square inch, PSI, same units. And let's assume that we have x-axis, y-axis pointing in the plane of the paper, and z-axis is up by the right-hand rule. If you do x cross y, you should get z. Okay, now if this assume that this plate is loaded in such a way that it induces all stresses possible. So in this case, there's a normal stress, there's a shear stress tau z y tau z x. So these are called Cartesian stresses because they act, so to say, in the Cartesian direction. They're resolved in the x, y, z axis. You could also have polar stresses and so on, but in this case, we're only interested in stresses which can be best represented along the x, y, z direction. Okay, so why did I write zy and zx? What's the notation about? So here is how you can interpret tau ij. I gives you the normal to the plane, and j gives you direction of stress, direction of shear force or stress. Okay, so how is that linked to what I have shown here? So I have z here. So that indicates the normal to the plane. That means that it's acting in the plane, this plane. Okay, the best way of representing a plane is through the normal to the plane. The normal to the plane is z, and that's why I have tau z. Okay. And then the second one gives me the direction, so y. So this is in the y direction. This one is in the x direction. And then sigma z, sometimes people write it as sigma z, sometimes people write it as sigma zz, but the two z's don't really have any much value because normal stress always acts normal to the z plane and the direction is always z. So you could just use one variable, not two. So sigma z is probably simpler than writing sigma zz. Okay, so that's sort of the notation we'll be using. Now that we have that in place, so remember that the first one gives the plane and the second one gives the direction. Let's move on to plane stress element, which will be used later on when we talk about Mohr circle. Okay, we'll be looking extensively at plane stresses, which means that these stresses are in the plane. Will hardly go to 3 dimensions. This is useful because many times we're designing things which are thin, and so we really don't need to deal with 3D stresses. Another way this could be used is if you have a 3D object, you can think of analyzing it in planes like the XY plane, the YZ plane, and so on. So here is some point on the object which we're trying to analyze for stress. Really, it's a small point, but I'm just blowing it up to be a rectangle. So it's easier for us to see and use it for calculations. Okay, so now there are stresses. Well, this is in the XY plane. Okay. Okay, and then maybe you can help me here. Okay, these stresses which I've shown are clearly normal stresses. So what should I put for the subscript? Should it be, there's only 3 options, sigma x, sigma y, sigma z. So what should I put here? What should go here? There's only 3 options, x, y, and z. So always you put something which is, the way to think of this is, if you go back, this is the stress in the z direction. So similarly, this should be the stress in the x direction. And this one is also the stress in the x direction because it's pointing, well, it's pointing in the negative x direction, but still in the x. Okay, now it's not hard to see that this should be y, but it's pointing along y. Okay, so this is one thing. The second thing is the shear stress. Okay, now this is probably a little bit more harder. There's a tau here, and I need to put two things here. There's a first part, second part. The first part gives me the plane over which that stress acts. Okay, so that plane is this plane, right? So this plane, again, when you represent a plane, the best way to represent a plane is to normal to the plane. The normal to that plane is x. So the first one should be x. And you can see that the second one should be the direction of the shear stress. So that's along y. Okay, it turns out that this one will also be the same. It's be tau xy. Because it's in the x, the normal is x and the direction is y. This one, which is on the top face, again, tau, there'll be two things here, the plane and the direction. You can see that the plane is this one, the top plane. The top plane has a normal in the y direction, so y. And then the direction of this stress is in the x direction, so x. So this one, you can reason out the same thing. Okay, so this is something you probably have seen so many times when you, was this in strength of materials? Now, well, there's a derivation which I'll not go through, but it can be shown. Shown that the stresses in the x, y, and y are complementary, which means that tau xy is the same as tau yx. This is always true. And it's true because the rectangle shown cannot rotate. It's fixed. If it was rotating, that wouldn't be true. So they have to balance out. If you take the moments about O, you'll see that tau xy is same as tau yx. This is known as complementary shear. Tau xy leads to tau yx, and they're equal. Okay, so this is good news because for a plane stress element, we only have to deal with three stresses: sigma x, sigma y, and tau xy, or tau yx, whatever you want to call it. Just three, not four. Yeah, we've seen this before. Elastic strain is epsilon. It's if you have, let's say, a beam subjected to a force. If you apply a large enough force, this beam is going to stretch. So let's say the original length is L. The change in length, this one, is going to be delta L. Yes, so from that, we can write the strain. Let's assume that this is our x direction. So the strain in the x direction is delta L, change in length, divided by the original length. Now, if you want to compute the normal stress, one way of doing that is to use the strain and multiply it with Young's modulus. E is Young's modulus. This is a material constant, which means that it's fixed for the material. If it's steel, it'll have a certain Young's modulus. If it's bronze, it'll have something else, and so on. Now, it turns out that when you stretch something in the x direction, it's actually going to contract in the other two directions. So there'll be a strain in the y direction. It's actually, that symbol I think is nu. Is it nu? It's not nu. Yeah, it's nu. Nu times epsilon x, and Ez equals nu times epsilon x. Nu is called the Poisson's ratio. It's a non-dimensional number. This says that if the material stretches in the x direction, it will contract in the y and z direction. Non-dimensional constant. So these are some of the expressions you need to know. Okay, so that's for, so remember, this is just for one-dimensional, this is the 1D case. What I mean by 1D case is 1D stress. You're only applying a force, 1D stress case. You're only applying a stress in the x direction. Okay, now, in general, you could apply a stress in all the directions. Actually, let me, you know what, let me call this, instead of P, let me call it sigma x, just to make it connected with everything here. So let's call that sigma x. You just have to divide it by the cross-section area. Okay, now what will happen if you apply stress in the x, y, and z direction? So that's the generalization of this particular case, and I'll write that down. So this is going to be the 3D stress case, which would be something like this. Instead of drawing something which has length in the x direction, I'm going to draw a cube. And induce stresses on all the faces. So sigma x, this being x, this being y, and the z comes out. Sigma y, and the last one, this will come out. Sigma z, So each face would have a stress, a normal stress. Sigma is the normal stress. This is the strain. Okay, we can write the shear strain in the x direction as 1 divided by E sigma x minus nu sigma y plus sigma z. Strain in the y direction as sigma y minus nu sigma x plus sigma z. Strain in the z direction as 1 divided by E sigma z minus nu sigma x plus sigma y. Okay, now if you want, you can actually derive the same expression I wrote on the previous page from these expressions. Shouldn't be hard. You can put sigma x sigma y and sigma z equals to 0, right? From this figure, if you go here, there's only sigma x, there's no sigma y, sigma z. If you put sigma x as not 0 and put sigma y equals sigma z equals 0, you'll actually derive the same expression you had for the previous page. So this is a generalization. It helps you to, if you remember this, you can solve other special cases. So this is more general than what I had earlier. I wrote it down so that you are more familiar with, if you're familiar with the 1D case, this might help you to build the intuition. Okay, the last thing is shear strain. Yeah. This is, you mean this one? Yeah. Yeah. Poisson's ratio. Shear strain. So the best way to think of this is assume a block which is glued to the ground. And what we do here is we subject this block to a shear stress. Okay, there's as a result of the shear stress, and because the block cannot slide, it's glued to the floor, it'll actually twist or shear, and it will look. So this is really exaggerated. So it will shear like so. This angle at which it shears is gamma, and gamma is the shear strain. Gamma can be obtained from tau if you know G, which is also known as the modulus of rigidity, or it's also known as the shear modulus. Okay, it also turns out that you don't really need to know all the things, E, G, and nu. They are all related. E is 2 times G plus 1 plus nu. So you can compute G from E and nu, or nu from E and G, and so on. This just shows that shear strain is probably related to normal stress. I don't remember this derivation, but it's something which you probably might have seen before.